Now we also want to be able to understand how the graphs of parabolas are related to their quadratic functions. Now the general form, in this case here, the general form of a quadratic function is represented in the following way. It is f of x, which is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. Now, if the leading coefficient, which is a, if it's greater than 0, then the parabola is going to open up. If a is less than 0, then the parabola opens downward. And we can use the general form of a parabola to find the equation for the axis of symmetry. Now, the axis of symmetry is defined by x, which is equal to negative b over 2a. So that means we have the value of b here divided by 2 times the value of a, and then we have it being multiplied by a negative sign. Now, if we use the quadratic formula to solve ax squared plus bx plus c equals 0 for the x-intercepts, or also called the zeros, we find the value of x halfway between them is always x is equal to negative b over 2a, which is the equation for the axis of symmetry. Now, if we take a look at the figure 4 here, okay, it's going to represent the graph of the quadratic function written in the general form, where y is equal to x squared plus 4x plus 3. And what we want to do is we want to identify what are the values of a, b, and c in this particular equation. So in this form, we can recognize that the leading coefficient is a 1, so therefore a is equal to 1. We can see that the second coefficient, which is the middle number here, b is equal to positive 4, and then we can see that the value of c is equal to positive 3. Now, because the value a is positive, meaning that it's greater than 0, then the parabola opens upward. Now, the axis of symmetry is x, which is equal to negative the value of b, which we determine is 4, divided by 2 times the value of a, which is 1. So if we go ahead and then figure that out, negative 4 divided by 2 times 1, which gives you negative 2. So we can say that the axis of symmetry is equal to negative 2. Now, if you take a look here at this line, this dotted line, well, that is considered the axis of symmetry, which is going through the value of x is equal to negative 2. Now, this also makes sense because we can see the graph of the vertical line that we can see here that divides the graph in half. Now, the vertex always occurs along the axis of symmetry. So for a parabola that opens upward, the vertex occurs at the lowest point on the graph. And so for this scenario here, there is your vertex. And that vertex is the following. If we move to the left 2 x units and then down 1, which is negative 1, we would get a vertex of negative 2 comma negative 1. Now the x-intercepts, those are the points where the parabola crosses the x-axis. So in this particular example, it crosses the axis at 2 points. One point is at negative 3 and 0, so therefore there's one x-intercept. And then the other one is located at negative 1, 0. So therefore those are the x-intercepts. Now we also have what we call is the standard form. Okay, so the standard form of a quadratic equation is written in the following way. You have x, f of x, which is equal to a times x minus h squared plus k, where hk is the vertex. Now, because the vertex appears in the standard form of the quadratic function, this form is also known as the vertex form of a quadratic function. So as in the same case with the general form, if the value of a is greater than 0, then we know the parabola is going to open up, and the vertex is the minimum. If the value of a is less than 0, then the parabola opens downward, and therefore the vertex is a maximum. So figure 5 is going to show the particular parabola of this particular equation, which is y, which is equal to -3 times x plus 2 squared plus 4. So we know that the value of a is negative, so you can see that the parabola is opening downward, which means that we have a maximum. Now, since x minus h, meaning the middle part here, if you can see up here, this is x minus h, which is also down here, which it says x plus 2. So x minus h is in the version of is equal to x plus 2. And if we solve for h in this equation, we can eliminate x and then divide by -2, which means that h is equal to -2. So therefore, we can at least see the first part, or the x-coordinate of the vertex, which is -2. So in this form, we know that a is equal to -3, we know that h is equal to -2, and we know the value of k is equal to 4. And again, because a is less than 0, then the parabola opens downward, and so we have a vertex located at -2, 4. Now, the standard form is useful for determining how the graph is transformed from the graph of y equals x squared. And if you look at figure 6, we can see the graph of the basic function, which is y is equal to x squared. And so what that means now is that if you have a value of k that's greater than 0, then the graph is going to shift upward. Whereas if k is less than 0, then the graph is going to shift downward. And so if we take a look back at figure 5, we notice that the value of k here is greater than 0, and k is actually equal to 4. So therefore, what we've done is we've taken this parabola and we've shifted it up 4 units. Now, if we also look at figure 5 again, we can see that the value of h, which is the value of 2, positive 2, we have now shifted this graph to the left 2 units. And the magnitude of a indicates the stretch of the graph. So if the absolute value of a is greater than 1, then the point associated with a particular x value shifts farther from the x-axis. So the graph appears to become narrower and there is a vertical stretch. But if we have the absolute value of a which is less than 1, the point associated with a particular x value shifts closer to the x-axis. So the graph appears to become wider, but in fact there is a vertical compression. So in figure 5, the absolute value of a was greater than 1, so the graph becomes narrower. And now the standard form and the general form are equivalent methods of describing the same function, meaning that they're equal to each other. And we can see this by expanding out the general form and setting it equal to the standard form. So here you can see we have a times x minus h squared plus k. And what we do is we FOIL x minus h squared and then multiply it by a. And we get ax squared minus 2ahx plus ah squared plus k, which is equal to ax squared plus bx plus c. Now you can see here that we grouped this part together and the beginning 2 terms here together. So for the linear terms to be equal, the coefficients must be equal. So what we're saying here is that negative 2ah x is equal to the value of bx. Because they have the same variable part in x, we can say that negative 2ah is equal to b. And now if we solve for h, we divide both sides by negative 2a. So therefore h is equal to negative b over 2a. Now the axis of symmetry we defined earlier is setting the constant terms equal. So if you look what's grouped here, we have ah squared plus k. These are all constants, arbitrary constants. And the constant on this side is the value of c, which is the reason why we have ah squared plus k equals c. And so now if we want to solve for k, we can then subtract AH squared to both sides. And then what do we know about H? Well, we know that H is equal to negative B over 2A. So if we plug that in and then square it, then we would get B squared over 4A squared, and then we can eliminate one of the A's, and so we end up with C minus B squared over 4A. So in practice though, it is usually easier to remember that K is the output value of the function when the input is H. So f of H is equal to K.